Yes,
I think
ma'am, I will present very shortly again. There is a now the event is going live.
Yeah,
So
right.
yeah, so once again, I think there were a few more participants by the time we went live, and once again, I heartily invite Dr. Navid Kaur to this IAStructE webinar series. Dr. Navid Kaur is a scientist at the Central Road Research Institute, and she is the prestigious holder of the DST award. Many publications and many lecture series are to her credit, and we are very happy to have such an accomplished speaker here. So let us start now without much delay. We look forward to your session, ma'am.
Thank you. Thank you, Dr. Anil, for this brief introduction. Um, well, I'm really happy to be here to deliver this e-lecture, and I'm also excited because this is my first e-lecture. So, shall I start with the presentation? I think it's already 5 minutes.
Yes, you may. Yes, you may.
So I'll share my screen. Mm. So, is it visible?
It is visible to me. Maybe can we hear from one of the participants? Can you chat if it is visible clearly? Is the present visible? Okay, thank you so much, everybody. I think, ma'am, they have confirmed that they are able to see that.
Okay, okay. So, again, welcome you all for this lecture. I'm Naveed. I'm working as a scientist in CSIR CRRI. So, today I'll be talking about structural health monitoring. That is the science behind the safety of structures, right? So, I have deliberately kept this presentation assuming that there will be a mixed kind of audience. So, it consists both of basics as well as its application in the field. So I hope by the end of this lecture, you will be having some a sense of health monitoring and how the sensors, how the techniques, which techniques are used. So I assume by the end of this lecture, you will be having some knowledge about it. Okay, so before we dive deep into the presentation, let me first introduce you with the SHM experts. So, structural engineers, they are the people who design and build the structures around us, right? Electrical and electronics people, they are responsible for building sensors which we see around us. And data processing, they are the people who have the capability of handling huge data, right? So, the legends who have all these three expertise, they are the SHM experts. So I relate structural health monitoring very closely with the human health monitoring. For example, if a person is sick, what he'll do is go to a doctor, and the doctor will run so many tests on the sick person. He'll use so many medical equipments to monitor the body parameters, right? So what are the body parameters here? BP, sugar, temperature, and so many. So the doctor will analyze these parameters, and based upon these parameters, he will suggest some treatment, right? On the similar lines, we have structure health monitoring. Say a structure got some damage. Of course, the structure cannot go to the expert, but the SHM expert will go to the structure and see, use different kind of sensors and techniques and monitor the structural parameters. Now, what are the structural parameters here? Deflection, strain, acceleration, temperature, corrosion, right? So these are the structural parameters which the expert will monitor and accordingly suggest a treatment for the structure, right? So in this presentation, we will be confining ourselves to the sensors, techniques, and the different parameters. We'll not be talking about the treatment in this lecture, okay? So we are fortunate that our human body is blessed with self-healing capabilities. However, unfortunately, not the structures. You cannot expect the Leaning Tower of Pisa to restore its position without human intervention, isn't it? So, this again highlights the importance of SHM experts. So, the agenda which we'll be following in this presentation will be first talking about what is health monitoring, structural health monitoring, and why it is important. Then we'll be talking about different kind of sensors which are used in SHM, the conventional sensors and the smart material based sensors. Then the techniques which are used in SHM. Then what is the status of SHM? After this, we'll be covering the R&D work in the area of structural health monitoring, specifically using the piezo transducers first, then using the non-contact type techniques, including the radar interferometry technique, digital image correlation, which we frequently call DIC. Then we'll see what are the recent advances in structural health monitoring. We will here cover the drone technology, its integration with the artificial intelligence, then smartphone-enabled wireless, etc. And finally, we'll wrap up the presentation with the challenges which have blocked the SHM, which have not made the SHM to reach where it should have been till now. Okay, let's start. So the formal definition of SHM is estimating the state of the structural health and detecting the changes in the structure that can affect its performance. Right? So it has three components. First is the condition monitoring. Here we assess the present condition of the structure. So this is actually one time. So on spot we assess the structure's condition. So here we generally see the concrete strength of the structure, its integrity, we measure the load carrying capacity. So basically this is one time and it is a sort of subset of the SHM. So it is one time. Then the structural monitoring is kind of long term. So here we install sensors on the structure and keep on monitoring them for longer period of time. So this is more of maintenance. This is more inclined towards the maintenance to maintain the functional utility of the structure, right? And the third is structural control. Here we monitor the dynamic response of the structure using different devices like friction dampers, viscous dampers, tune mass dampers, base isolators, and so on. So the idea is here I have taken the example of tune mass damper, which is installed in the Taipei 101 skyscraper in Taiwan, which was the tallest building till 2010. So just to give you a sense how big these structure control mechanisms can be. So this is the tune mass damper, which is actually installed in that building. So it is visible from the 88th floor of the building. So there is actually a view gallery there. You can see the tune mass damper. So it is a big ball weighing around 660 tons. It's a steel sphere ball. So this video is captured during the Typhoon Phoenix, which happened in 2014. So you can imagine how big these control mechanisms sometimes can be. Now the question is, why do we need SHM? Now, if a doctor commits a mistake, it will cost only one life. Unfortunately, but an engineer's mistake can lead to so many lives. As per a report by NCRB, which was published in 2015, almost 8,800 lives has been deaths have been caused due to 117 bridge collapses. So when a human life is associated with something, it becomes really precious and it has to be well taken care of. I have another example just to show you the importance of SHM. That's the Columbia Space Shuttle disaster, which happened in 2003. It happened, as per the NASA's report, it happened due to a small piece of foam from the fuel tank. It hit the left wing of the space shuttle. So we'll see this video to see the sequence of events which happened that day.
January 16th, 2003. Liftoff of Space Shuttle Columbia with a multitude of national and international space research experiments. Investigators now know that during launch, a piece of foam no bigger than a briefcase breaks off from the fuel tank. It crashes into the wing and blasts a hole around 25 centimeters in diameter. February 1st, 2003. 50 minutes to disaster. Mission Control gives the Columbia crew the go-ahead for re-entry. What nobody knows is that the outer skin designed to protect them from the fearsome heat has a fatal breach. 16 minutes to go. Columbia hits the Earth's atmosphere at almost 28,000 kilometers per hour. The leading edges of its wings reach 1,400 degrees Celsius.
That was amazing. It's really getting really bright out there. Wow. Like a blast furnace.
9 minutes. The data recorder reveals that the gaping breach in Columbia's left wing causes drag on its left-hand side. Superheated gases penetrate the wing at 4,400 degrees Celsius. Heat sensors in and around the area show extreme temperature spikes. 6 minutes left. Now temperature sensors start to go offline as superheated gases burn them out.
See, the shuttle was not equipped with any NDE system. So just based upon the computational analysis, the ground team gave the go-ahead for the re-entry. So it shows that we really need NDT systems for the proper monitoring of the structures. So now we got the answer why we need SHM. So if you want to talk about structural safety, the answer is SHM. If you want to reduce the risk during the excavation, you should go for SHM. For avoiding the leakages in the pipe structures, it is required. Definitely, it's a replacement for the visual inspection, which can sometimes be very risky and even impossible in the inaccessible regions. For the retrofitting evaluation, this is required. And finally, for the design validation, SHM is must. So unfortunately, even a car costing few lakhs is equipped with so many sensors. However, we civil engineers, we seldom bother to validate our designs after construction. Okay, so now we'll see the sensor technology. So here I have considered a list of conventional sensors and smart material based sensors. Conventional sensors, basically they are the ones which are more frequently used in the SHM of the structures. But I'm sure the list is huge. Apart from the one which I have considered, there are so many sensors which are available in the market. But let me tell you one thing, that none of the sensors measure the structural parameters directly. However, they measure some electrical quantities. For example, most of them measure voltage. So that voltage is actually calibrated to give you the structural parameters in the terms of strain, deflection, temperature, corrosion, and so on. So the most important thing here is the calibration constant. For example, if we take the example of electrical and vibrating wire strain gauges, here the voltage is calibrated to give you the strain. So if I want to calibrate that output voltage to give me temperature, it's only the calibration constant which I have to change, right? So all the sensors, the most important thing is the calibration constant. Okay, so we'll take all of them one by one. First is electrical strain gauge. So you can see here, this consists of a small thin wire which is moving around like this. So this it is very fragile. It's very very delicate sensor. So you just consider a beam. You attach this strain gauges on the bottom of the beam. For example, if you bend the beam, the length of this sensor of this wire will actually change. So as the length of this wire will change, its resistance will change. So that change in resistance is actually calibrated to give you the strain values, right? So that's the principle on which it works. The problem with these sensors is that they are very fragile. So I don't prefer, I wouldn't suggest you to use these kind of sensors for the field applications. However, they are quite inexpensive and they are very easily available. So they are actually mostly used in the for the strain measurements, the electrical strain gauges. Another type of sensor which is used for strain measurement is the vibrating wire strain gauges. So they are actually very robust and they are very frequently used for strain measurements in the site applications. So this is how it looks like. So this part, you can see the ends of this sensor. So this is attached to the structure. It is surface bonded. Even the embedded vibrating wire strain gauges are also available in the market. So this, again, you attach this vibrating wire strain gauge on the bottom of the beam, and it consists of a very thin vibrating wire. You see, there is a vibrating wire here. So this wire actually runs from this point to this point. Okay. And for example, when you energize this sensor, there is a vibrating sensor. When you energize it, it will pluck this wire, right? This vibrating wire, it will pluck it, and this vibrating wire will start vibrating just like a rubber band. Okay. So the frequency of this vibrating wire is actually calibrated for the strain measurements here. Now, if you say attach this vibrating wire strain gauge at the bottom of the beam and the beam is deflected, the length of the wire, which is running from here to here, that will change. So its vibrating frequency will also change. Thus, you can calculate the strain in the terms of change in the frequency based using this strain gauge. I have already covered the pros and the cons. Yeah, its problem is that this sensor can only be used for static strains, not for the dynamic. The previous one, this one, electrical, it can be used for the dynamic measurements also, but this cannot be used. Okay, so next sensor is the linear variable differential transducers. So we very frequently call them LVDTs. These sensors are used for measuring the displacement. The previous one were for the strain. So they are used for measuring the displacement in the structures. Now they work on the principle of electromagnetic induction. This is the same mechanism which is used for wireless mobile charging. So I'm sure some of you might have heard about it. So wireless mobile charging, let's see how it happens. So in the charger, there is a primary coil. Okay? So this is the primary coil. So when you give AC supply to the charger, the electrons will start moving it around it, and it starts generating an electromagnetic flux. So this is the primary coil generating the magnetic flux. Now, if you bring your mobile phone near this charger, your phone also has a similar smaller secondary coil. So when you bring your bring your phone near the charger, a resulting flux will get generated in the secondary coil. Okay, that causes the electrons to move in the coil, and which results in the charging of your mobile phone. So this is the electromagnetic induction. Its similar principle is used in the LVDT sensors. So this is how it looks like, the sensor. So this probe is actually attached to the structure. For example, you again consider a beam. This probe, the end of this probe will touch the will touch the bottom of the beam, and it can move inside the sensor. Okay, so if you cut the cross section of this sensor, it will look something like this. So it has a primary coil. The blue one is the primary coil, and the red one are the two secondary coils. They are identical. They have the equal number of turns. So these coils are wrapped around the movable core. So this probe is actually attached to a core inside it. So this can move in this two-way direction. And to understand the principle, this is how it will look like. So you apply AC supply to the primary winding. So it will generate the magnetic flux. Since these are the two secondary windings, so the resultant indux will get generated in the secondary windings. Now, when the core is at the central position, there is no differential electromotive force across these two secondary windings. And when it moves in either of the direction, a voltage will be generated due to differential EMF across these S1 and S2 secondary windings. Now that voltage is actually calibrated to give you the displacement in the structures. Next type is the load cell. They are pretty simple. So the very basic example of their application is in the weighing machines. But this is the load cell which is actually used for the structural purpose. Here you can see it is used for measuring the pre-stressing force in the PSC girders, bridges. So it consists of two strain gauges. So when you apply load on them, the strain gauges will get deflected and they'll produce voltage, and that voltage is calibrated for the load values. Next sensor is the thermocouple. Now this sensor is used for measuring the temperature in the structure. Most of the time it is embedded inside the structure, and usually we tie it around the reinforcement. So it works on the Seebeck effect. Here in the Seebeck effect, what does it say? That if there are two dissimilar metals, two different metals are there, and you connect their one end, right, and heat that joint end, then the electrons will start moving towards the colder end. Since these are two different metals, so there is a tendency that the speed of the electrons moving towards the colder end, that will vary depending upon the conductivity of the two metals, right? So since the electrons which are reaching at the colder end, they are different, so there will be a voltage difference across this end. So that voltage difference is calibrated to measure the temperature. Now, can you tell me if these two metals are instead of different metals, they are same? What will be the output here? Yes, you're right. It will be 0 volt because equal number of electrons will be moving towards the colder end, and there will be no voltage difference across this end. So no voltage reading across this point, and so we have to use two different metals. Another important point which I would like to make here is how they should be, how these sensors should be embedded inside the structure. For example, again consider a beam. So you have to make sure that the thermocouples are not inclined at any angle. So they should be plane. They should be residing in one plane. So okay, so they can move in their own plane, but they cannot be inclined. They cannot make. They should not make actually any angle with the horizontal. This is because the temperature of the structure varies across the depth. So if you have or maybe by mistake it is kept like this, then the results will be erroneous, right? Okay, next sensor is the corrosion sensor. So to understand the corrosion sensor, first we have to understand corrosion and how it happens. Okay? Now say you consider any metal except the pure ones, for example the gold. All these metals, they undergo lot of machining process in the refineries to convert them into the form which they are actually in which they can be actually used. So during that process, huge amount of energy is infused in these metals. So corrosion is nothing but taking that energy out from these metals so that they can attain their stable state, so then they can come back to their natural state. So corrosion is nothing but bringing that energy, taking that energy out from the metal. Now how it happens, considering any RCC structure, so as the pH of concrete is very high, so that high pH results in a passive layer around the rebar. So that stops the corrosion of the rebar. But when the concrete is exposed to very harsh environment, this layer get destroyed and the corrosion happens. And how? Let me tell you how. So while processing of the metal, there are some regions in the metal which are having very high density of electrons and some are having low density of electrons, right? So the higher density electrons, that part of the metal becomes the anode, and the lower density part region becomes the cathode. And of course, there is a metallic path. Now for corrosion, we know that we need four things: anode, cathode, metallic path, and an electrolyte. Now electrolyte is nothing but a fancy name for water, right? So when the concrete is in touch of water, when there is water inside the concrete, you get the electrolyte also. Otherwise, anode, cathode, and metallic path was already there in the concrete structures. So when you got the electrolyte, the electrons will start transferring from the higher concentration towards the lower concentration, and that results in the corrosion. Now, again, we have to note one point here, very important point, that the corrosion always happen at the anode. That is from where the electrons are leaving. Okay, so always the corrosion happens at the anode. So this is how the corrosion sensor looks like. So it has different anodes, you horizontal bars which you are seeing. These are the anodes. So this process is called cathodic protection. What is happening here is, so you apply you provide an external anode in this process. You apply current to this anode, and that results in transferring the electrons through the electrolyte. Now, I generally explain this process with an example. You consider a small door, okay, from which only one or maximum two persons can come out of that small door. Okay. Now, in front of that small door, there is a huge, big door from where thousands of people are coming in an opposite direction, right? Now, that huge rush of people will have the tendency to block the one or two people who are coming from the small door. Can you visualize that problem? See, so those one or two people, they cannot come out because the other people are coming in opposite direction. The same thing we are doing here in the cathodic protection. We are actually shifting the corrosion from the rebar to the external anode. What is happening here is this anode is now a bigger door, which I gave you the example of. So this anode will act as bigger door from where lot of electrons are coming because of AC supply. So these electrons will transfer through the electrolyte to the cathode. Okay, so we shifted the anode from here to here. This is why, so corrosion is not, we have not stopped the corrosion. We have shifted it from the rebar to the external anode. So this is why we call this process as sacrificial anode cathodic protection. So because this anode is getting corroded during this process. Okay, accelerometers. Next sensor is accelerometers. Now, I would say these are the most amazing sensors because they have revolutionized so many things around us. You name any application, name any area, it will have its application there, right? Be it measuring the acceleration due to gravity experienced by a spacecraft, to measuring the speed of a car using your smartphone which is in your hand. So it has its application in robotics, construction industry, aerospace, gaming, and the list is long. So even the inflating of the car bag, this airbags in your car, that is also happening because of accelerometers. So let us first revise our basics. Okay. So what is acceleration first? Now, I'm sure all of you must be aware of its definition, that it is the change in velocity per unit time, right? Now, can you measure the acceleration of a car if you are sitting in it, inside the car, which starts from a standstill condition? Yes, you can. It is very simple. What you have to do is you just have to see the speedometer of the car and use a stopwatch. How? For example, the car starts from a standstill condition and attains a speed of 100 kilometers per hour in 5 seconds, right? So the acceleration becomes 20 kilometers per hour per second, which means that in every second the car has increased its speed by 20 kilometers per second, right? Now, this is not the way how accelerometer measures the acceleration. So it is rather based on the Newton's second law of motion. So which says if you can measure the amount of force required to move a unit mass, so force is equal to mass into acceleration, based upon that, then you can measure the acceleration. And from this setup, from this spring mass configuration, we also know using the Hooke's law that the force is equal to spring constant into the distance displaced by this spring. Now, if you use these two equations, you will reach here. And in this equation, if you can somehow measure the x value, the distance traveled by the displacement of the spring, rather, you can measure the acceleration, because mass will be known and the spring constant will be known. So you just have to measure the displacement in the spring, then you can measure the acceleration. So based upon this philosophy, there are 3 different type of accelerometers: mechanical, capacitive, and piezoelectric accelerometers. So in all of them have a housing in which there is a small proof mass and a small spring, and the mass is actually attached to the housing using a spring. So in the mechanical system, there is a pen attached to the proof mass, which will leave traces on the paper when this accelerometer experiences any vibrational force. So this was actually used for the seismometers for measuring the earthquakes. Second type is the capacitive accelerometers. Here you have 2 capacitor plates. So when the vibrational force is exerted on the accelerometer, the housing will move, and this proof mass will move, and this will reduce the distance between the capacitor plates. So this will change the distance in the capacitor plates, which will change the capacitance of the plates, and that can be used to measure the distance and thus the acceleration. In the piezoelectric materials, there is a small piezoelectric crystal attached to the proof mass. So when it experiences the force, external force, so the ball squeezes the piezoelectric material, that causes a small voltage, that results in a small voltage, and that voltage can be used to measure the deformation in the piezoelectric material, and thus we can measure based upon that deformation, we can measure the acceleration. Okay. So the accelerometers which we have just seen, they are quite bulky. Rather, I would say the micro electromechanical system, the MEMS based accelerometers, they have actually changed so many things around us. So these are the sensors, accelerometers, which are responsible for the screen rotation. You have your smartphones. So these are the screen rotation in your smartphone is actually happening due to these MEMS accelerometers. So let's see how it is. So it is again having the same type of fundamental parts which we just saw in the previous accelerometer. So there is a housing, and this comb-like structure is actually the proof mass, right? So it is vibrating like this. So the flexibility of this mass is giving you the spring parameter here, spring component. So if you zoom the three fingers, so these are the green ones are the capacitor plates, and as the proof mass is changing, vibrating in between this, so it is causing change in the voltage. So that voltage is actually calibrated for measuring the acceleration. So in the conventional sensors, this is the last sensor, tilt meter and inclinometer. So they are used for measuring the angles with respect to the gravitational force. Now this is the tilt meter, and they work on the principle of plumb bob, which I'm sure you all must have seen. So they have these accelerometers inside them. So and these two detector plates. So if there is any inclination, so the voltage across these detector plates will change. That will be calibrated to give you the angle, right? So this tilt meter can be used actually for both the vertical as well as the horizontal inclination of the surface. However, the inclinometers, I'll show you this video. In the inclinometers are basically only used for the vertical inclinations. Now they are used, for example, if you consider the any well foundation which are 20 to 30 meters deep, so you have to ensure the incline, if you have to ensure the verticality of this deep foundation. For those purposes, inclinometer is used. So we'll see how it is used. So actually this is the sensor. These are the balls. So this hole is the sensor. The wheels are used to keep these sensors in place. Sorry. So this casing will be going throughout the well foundation. This yellow casing will go throughout the wall of the well foundation. So in this way, you will keep on sending the sensor throughout the depth of the foundation. Once it touches the bottom, then you will start taking its readings, and you keep on taking its readings. So for every time you will make sure that the readings are same to ensure there is no angle inclination. Okay, so now we are done with the conventional sensors. Next is smart materials based sensors and actuators. So what are smart materials first? So these are the materials which have the ability to change their physical properties in a specific manner when a specific type of stimulus is applied across them. Now in till 1990s, the word smart and intelligent was used interchangeably for these materials. But then in 1988, during a workshop which was held in US Army Research Office, it was decided that the word intelligent is actually associated with a very high level cognitive skills. So the materials which are till now available, they do not match with that level. So it's not correct to use the word intelligent. So then afterwards, it was decided that only the word smart will be used for these materials. Right? Now, if we are calling them smart, you can ask me, why are they smart? Okay. You consider any material, and if you apply load on these materials, there is a tendency that the material will get deformed. Okay, so that mechanical deformation, only the normal conventional materials, mechanical deformation will happen. However, in the smart materials, along with the mechanical deformations, there are some other effects. For example, in the piezoelectric materials, along with the deformation, there is a charge generation as well. So in these materials, there is always a coupling effect. Okay? So because of this, they are smart. Now, if you're calling them smart, there must be a scale of smartness, isn't it? So the materials which are available till now, they generally are lying in the range of highly sensible to poorly intelligent level. So we'll take all the smart materials one by one. First is piezoelectric materials. Now they have, these are the materials, when we apply mechanical stresses on them, then they will produce electrical charges like this. So when you compress them, charge will be generated across these materials. And when you apply electrical charge across these materials, they will get deformed. So you see, electrical charge is applied across these materials, and they got elongated, right? So next is the smart memory alloys. These are the materials which regain their original shape when they are heated. Okay, so they have a property that they regain their original shape. We'll watch this video to understand how it's happening.
So in the previous video, I showed how the nitinol remembers its original form when it's heated up. Now, many people were wondering if you could tie it in a knot and would it revert to its original shape? Let's give that a go. So I tried a various array of different knots, and from what I've noticed, it kind of works. Even though I couldn't get the knot as tight as I wanted because it's made from metal, it's still pretty impressive.
So this is nothing but just the hot water. So he has the actual shape of this memory alloy is a pin. So whatever shape you give this after deformation, and you put it in the hot water, it will regain its original shape of a pin.
Okay, let's try something else. So here's a new batch of nitinol, which I have some more wire around the top of a can and heated it to set a circular shape. And now, when I heat up this pathetic excuse for a triangle, it reverts back to a circular shape. Interesting. Now for this last test, it's just a bit of fun. I scrumpled up a big bunch of straight nitinol and threw it in a jar of hot water, just to see what would happen really. Here we go. And it kind of looks like a spider's web.
Okay, so its applications are in biomedical field. So these self-expanded stunts have been rigorously these days used for the surgery purposes. Then these eyeglass frame, flexible frames, and this is the space rover wheel. Now the spacecraft which was used for the rover which was used for the Columbia, I forgot the name of that. So these materials, they have a very super elastic nature. That is why they can withstand the damage due to very sharp rocks. So the NASA people now, they are trying to replace the wheels of the rover with this smart memory alloys. So next type is the electrorheological fluids. So they have the property that when electrical field is applied across these materials, their viscosity changes. So let's see how. So in this position, there is no electric field applied currently. I see electric field is applied and its viscosity changed. So it has its application in the dampers, shock absorbers, and these days in human prosthetics also. Next type is the chromic materials. So these first is the thermochromic materials. So when these materials are exposed to temperature, they change their color. In the photochromatic materials, they change their color when they are exposed to light. And the electrochromic materials, these materials change their color when they are exposed to different voltages. Now, if you compare the properties of different smart materials, few of the smart materials that are rigorously used, first is the PZT, which is the piezoelectric material. This is another type of piezoelectric material only, and the magnetostrictive materials and smart memory alloys. Now, the free strain, which is there in the PZT materials, is pretty good. So it is ppm is basically microstrain, so 1000 microstrain. And magnetostrictive material, it is 2000, but in SMA it is 20,000. So this makes SMA as a very good actuator. So its application is more in the actuation part. Of course, the piezoelectric materials they also have a very good free strain, so they also have the actuation properties. And if we see the elastic modulus, all of them have comparable values except the PVDFs because they are flexible materials. Then if you see the frequency band, now PZT materials, they can operate in very high frequency band as compared to the other materials. The SMAs, they have very low frequency band, so definitely they cannot be used as sensors. So this is the reason why piezoelectric materials can be used both as actuators as well as sensors. So in this presentation, that is why we will be focusing only on the piezoelectric materials among all the smart materials which I have just till now covered. Now, piezoelectric materials, it is made up of two words, piezo and electricity. Piezo is a Greek word which means to press. So pieson, which means to press, and electricity means ember. It means when you press these materials, electricity will be produced, right? So how it happens? Now, for any crystalline material, if it is polycrystal, then only it can be piezoelectric, because in monocrystal, all the crystals are unidirectional. However, in the polycrystalline materials, all the crystals are directing in different directions. So they have got stabled in a way that there is no resultant charge. So they are in stable condition in this condition. But to convert them into piezoelectric materials, what you have to do is you have to apply an electric charge and you have to heat them till the Curie temperature. What will happen? All the domains will start directing towards the electric field direction. So even if you remove the heating, then also they will remain in the same direction of the electric charge. So this is its polarization direction, right? So this is how piezoelectric material is made. Now, when you press these materials, when you deform these materials, electrical charge will be generated, because these crystals will start getting displaced from their position. So that results in generation of charge. Okay. So next is SHM techniques. So in this presentation, I have given a huge list, but we'll be covering only the global technique and the local EMI technique, which are relevant to the piezoelectric materials. So the main difference between the two techniques is that in the global technique, the whole structure is acting as one structure, and we apply loads on it. However, in the local EMI technique, only a small region is the concentrated part where we monitor the structure, right? So we'll take them one by one. In the global technique, there is a structure, and we apply dynamic loads in terms of impact or shakers, but the load should be dynamic since it's a global dynamic technique. So when you apply load on these on the structure, and then you compare the modal responses. Now, what are modal responses? They are the natural frequency of the structure and the mode shape of the structure. So when you apply dynamic load on the structure, the the modal responses will be compared in the damaged and the undamaged state. So this technique is used when the level of damage is high, because the whole structure is acting as one unit, and this technique is working in the frequency range of less than 100 hertz. So only very bigger level of damages can be detected using this technique. Next is the local EMI technique. In this technique, we attach a piezoelectric patch to the structure, and we using this machine LCR meter will give a voltage of, will give a sine wave voltage to the PZT patch, which will cause the actuation in the PZT. I told you PZT patch can act as both actuator as well as sensor. Now in the first stage, when you have given the voltage, sine wave voltage to the PZT patch, it will start actuating, and it is acting as an actuator here. And since the PZT patch is attached to the structure, the surrounding structure will also start vibrating. Now in the second stage, the same PZT patch will start acting as a sensor, and it will sense the vibration of its surroundings and give the result in the form of conductance and susceptance. So we'll see how they will look like. Important thing here, another important thing which we have to see here is the frequency range. In the previous technique, the frequency range was 100 hertz, less than 100 hertz. So it was very low as compared to this, because here you see the frequency range is 30 to 400 kilohertz. So this is why, since the frequency is very high, this technique is very sensitive to very small level of damages. Okay. So this is the conductance, typical conductance signature of a structure in the undamaged state, and after damage it changes, and this is how we will compare the two stages of the structure. This is a relative technique, and the undamaged signature is just like the signature of a healthy body. So if like we have for a body, we have different parameters. We know that this is the range for the temperature when you are healthy, and if it changes, then we know there is some problem. So in the same way, if there is some problem, its healthy signature will get changed, and we quantify the change of this signature. Now, since last 20 to 25 years back, it was just a research project, research topic. However, it has now converted into a huge industry. But it has been identified as a crucial element. However, there are no codal provisions for this, for the SHM. No detailed cost-benefit analysis are available that has restricted its use. And also no certification is available for the SHM currently. So till now we have covered different type of sensors, different SHM techniques, and different and its current status. Now we will start covering the research work done in the field of structural health monitoring. First, we'll start with the SHM using the piezo transducers. So here, first is the integrated SHM and the energy harvesting. Now, as per the Prime Minister's vision of building 100 smart cities in next 10 years, so for any smart city, we need smart structures, right? Now, first is, what are smart structures? So any structure which can communicate any unacceptable change in itself to the concerned authorities within a safe time, that's a smart structure. Now, the continuous monitoring of these smart structures is important. For that, we might have to frequently change the batteries, but sometimes it becomes really cumbersome and maybe impossible if the whole system is attached in an inaccessible region. For that, with our rigorous research, we have developed a solution for this problem by using the dual nature of PZT patches. Because I told you the PZT patches, they produce voltage when you apply strain on these materials. So they have the energy harvesting properties as well. So using the energy harvesting and the structural health monitoring properties of the PZT patches, we have developed the self-sustainable system where the same PZT patch will be generating the energy as well as doing the health monitoring. So it can be used in several places which are inaccessible. Let's understand the concept here of the integrated SHM and energy harvesting. Now say you consider any structure where you have attached a piezoelectric patch. For example, we consider a bridge over which some vehicles are moving. Now because of the vehicle movement, there are mechanical vibrations in the bridge. Okay? So those mechanical vibrations will be converted into electrical energy using the piezoelectric material, and that electrical energy will be stored in some storing device. This is happening during the idle stage when no health monitoring is being done, right? Now, for say a damage has occurred in the structure, then the same PZT patch will be used for the health monitoring of the structure by using the stored energy which was stored during the energy harvesting stage. Right? So this is how the concept of energy harvesting is. So energy harvesting plates are planned to bond inside the road surface on which the vehicle load will be applied and the energy will be harvested. So some experiment which we have done in CRRI. So this is how the piezoelectric energy harvester plate was attached on the road surface and vehicle load was applied on it. Different type of loads were applied. A car which was weighing around 1 ton, then an SUV which was heavier than that, then a truck of around 7 tons. Different vehicular speeds were used for the experiment. So these are the energy generated from the piezoelectric energy harvested plate, and this is this energy stored using this energy storing circuit. So you can see here the energy generated by the piezo energy harvester was almost 6 to 24 times more than the energy stored. So we are currently working on improving the storage of the energy to store more maximum energy which we can. Next is the structural health monitoring part using the piezo sensors. So here we know that there are a lot of post-tensioning, there are a lot of losses in the PSC bridges which happen during the due course of, during the age of the PSC bridges. So what we have done is we have attached sensors on these anchor blocks to monitor the residual post-tensioning force in the bridges. So this is how the sensors were attached on the anchor block, and this is the, I'll just skip this. And these are the conductance signature during different stages of the post-tensioning of the bridge. And we generated the calibration curves which can be used for future estimation of the pre-stressing force. So now we covered the energy harvesting separately and the structural health monitoring using piezo patches separately. Now let's see how they can be integrated. This is AD5933 circuit, which is a very low power consuming alternative for the conventional LCR meter. So we were using this LCR meter for doing our structural health monitoring using the piezo patch. So this is a very low power consuming alternative for this. So in whatever the experiments which we did in the lab, they from those experiments we saw that for one time, if we are using this circuit, for one time SHM using this circuit, we require 10 hours of charging, right? So energy harvesting time required is 10 hours. However, if we consider a Delhi-Gurgaon expressway on which in 1 hour almost 1348 vehicles are moving in 1 hour, so the energy harvesting time will reduce from 10 hours to just 38 seconds. So if you attach these kind of piezoelectric harvesting plates in these kind of busy traffic road expressways, so energy harvesting time will drastically reduce. So next thing is determination of in situ early strength, concrete strength. Now, it is important to know what is the best time to remove the formwork in the casting yards to increase their construction or production rate. And also for the pre-stressing, for the pre-stressing girders, it is important whether the concrete has reached its perfect strength so that we can do the pre-stressing. For that, what we have done, we have given a solution where we can measure the in situ concrete strength, early in situ concrete strength using the piezoelectric sensors. So we have embedded the sensors inside on site inside the concrete, and we monitored the conductance signature of the piezoelectric patch, and based upon that we generated models and we estimated the concrete strength, and we found that day two onwards, the results of the predicted strength and the actual strength were quite matching. They were encouraging. So next was the post-tensioning force assessment in the PSC bridges. So in this experiment, what we have done is we attached the piezoelectric patches on a conventional load cell. So this is a load cell. Remember, I showed you its picture in the conventional sensors. So this is a commercial load cell which costs very expensive. So what we have done, we attached piezoelectric patches on this load cell, and we calibrated the piezoelectric patch to give us the load value. Remember, in the beginning I told you that any sensor will not give you the structural parameters. You have to calibrate it. As the commercial load cell is giving converting the strain to the load value, in the same way our piezo sensor is also not giving me the load value. I calibrated these sensors to give me the load values, and this is how it was attached on the site. And we again calibrated in the lab, and we compared the results with the commercial load cells, and except the one load cell, rest of the three load cells were giving good results. I mean, it's a very low cost alternative to the expensive load cells, I would say. So next is the retrofitting assessments using the piezo transducers. So in this experiment, what we did, we have given a deliberate damage in the beam. This is a 4-meter long RCC beam. So in this beam, we have done 4 level of damages, and then we did the retrofitting. So in the first level of damage, we removed the concrete. In the second level, we cut the first reinforcement and the second reinforcement, and then we welded the two in the retrofitting stage, and then we put the concrete back and retrofitting in the retrofitting stage 6. So we monitored the mode shape of the beam. So in the first stage, second damage stage, so it was rising upward because of reduction in the EI values, and then it again reached back in the retrofitting stage toward near its undamaged state. So next is the impact assessment using the piezo transducers. So in this experiment, we used 4 different type of sensors, piezoelectric sensors. First, these were the circular sensors and the square sensors embedded in the cement mortar and a adhesive layer. So this is how the sensors were instrumented in the slab. It was a 1 by 1 meter, 3 samples of slab were casted. And this is how the impact was applied on the slab using a steel ball. And this figure shows you the damage, pictures of the slab after this last impact, 7th impact, in which the material was lost. So all the 4 sensors were very successfully detecting the damage levels using the equivalent stiffness derived using the piezoelectric patches, piezoelectric sensors. And next is fatigue monitoring using the piezoelectric sensors. So in this experiment, the beauty of this experiment was that it was we did this experiment continued it for almost 1 year. So we applied very low level of strain using these using a shaker, and we monitored the stiffness values derived from the piezoelectric patch using in this experiment, and it was given a good sine S curve. Okay, so now we have finished the structural health monitoring using the piezo transducers. Next is health monitoring using the non-contact techniques. So in this non-contact techniques, we'll be first covering the radar interferometry technique. So here we were trying to measure the natural frequency of this pedestrian bridge, which is in front of the Okhla NSIC metro station in New Delhi. So this technique is based upon this radar interferometry actually. So we kept the equipment. It is a non-contact type technique. As you can see, we did not restrict the vehicle movement, and we kept the equipment in 2 locations. First, to measure the transverse measurements, to do the transverse measurements, and then to do the longitudinal measurements. These are some of the typical results. And also, we compared these results with the conventional sensors. We attached the piezoelectric sensors on the bridge and the accelerometers, and we compared the results of this radar interferometry with the accelerometer and the piezoelectric sensors. And they were the natural frequency was matching. And then this is a kind of preliminary work which we have done using the digital image correlation technique. This technique is based on the calibration of the different frames of videos. The problem actually with this technique is that the data which we get is huge. It's very heavy. So it is a video-based technique. So we have to capture the video of the whole beam during its destructive test. So we attached the conventional LVDTs at the bottom of the beam, and also we were capturing the video of the whole setup. And we actually, what we do here is we calibrate, for example, this to this. So we'll get the distance from here to here. We actually know the distance, and then in the frame we will tell that this line corresponds to the actual distance between here to here. So based upon that calibration in the video, this technique will give us the displacements which are happening in the beam. So we compared the results of the LVDTs and the DIC technique. So they were also appreciably matching. Okay. So next are the recent advances in the SHM. So here, first we'll cover the drone technology. We know that the currently the practices which we are using are the rope access ladders, and maximum we are using the mobile bridge inspection units, but they are many a times slow techniques and risky. So drone technology is basically a way which has revolutionized the visual inspection till now, I would say. So I think we are short of time. I will skip the videos. I have very nice videos of the drone. If time permits in the end, and if everybody agree, I'll just show you these videos. So these the drones have been used to be used inside the box girders. So this was the drone developed by Ilios by a flyability company. So I'll not cover. Will not. This is another drone which can go very close to the structure. So it is a L-shaped drone. It can even crawl as well as fly. So this can measure the cracks, crack width as low as 0.1 mm. So just quickly I'll show you.
As each wheel is independent, only zero exterior wall, the wall, we've enabled.
So next is the drone where people have tried using the contact type inspection. So whatever drones I have till now shown you, they were the replacement of the visual inspection. So here they have tried doing the UPV, I guess, but there is not much of information available regarding this drone. So I'll just this is how you can see there's a arm going out. So these are the UPV probes. This way, the drone will apply pressure and take the UPV readings. Okay, so next, this is a drone which is used to build a rope bridge. This is the work done by ETH Zurich. So I'll also play this video very quickly because we have already covered 1 hour, I guess. So in this way, I'll just move it quickly. So they are all computerized. Their movement is all planned. So this is how they are building the rope bridge. So it can take the load of a single person. This rope bridge, you can see. Okay. So in the this is the bridge where in China, where they have transported a 2-kilometer long cable of the bridge, cable for the bridge. So here you can see the drone is carrying a 2-kilometer long cable of the bridge. So I'll skip
Close to
this.
this.
Okay. So next is the R&D work which we have done in CRRI. We, along with our industry partner, we are developing a drone which can do both the visual inspection as well as the NDT, where we include in NDT we include the rebound hammer and the UPV. The first phase we have completed. So this is the bridge which we considered for our study. First, we collected the data using the drone, high resolution geo-referenced aerial pictures we took using the drone. Then we processed them in the 3D software, and then 3D model were generated using that software, and we compared the actual measurements with the measurements which we got from the model. So this is actually the model, and here we are measuring the actual measurements of the bridge. So we got an accuracy of 97%, and we like all other places also we were comparing the results. So 97 to 100% of accuracy we got using the so this can be used for also for the for generating the drawings where of the old bridges where no drawings are available. So we can use these 3D models for that also. Also for the visual inspection, for example, here water seepage, restricted bearing action. So we can use these 3D models for the replacement of the visual inspection also. Then next, in the next phase, we are customizing this drone for incorporating the NDT techniques. The previous results which I have shown you are for the for an existing drone, commercial drone, which do not have any payload. That is, it cannot take any extra load. However, the customized drone which we have developed, it has a payload of 600 grams. Now we are working on attaching a rebound hammer replacement, piezo-based rebound hammer replacement, which can be attached to this drone for measuring the concrete strength. The next is integrating the artificial intelligence with the drone technology. This I would show you quickly. So this actually works on the same principle like on face recognition. So we will make the software learn that this is the width and this is the length of a particular crack. So next time when it captures the picture of a similar crack, it will measure the length and its width. So this is the R&D work which is being done in Denmark. Okay, the last is smartphone-based enable wireless structure health monitoring. Wireless health monitoring is definitely being used all around. This is no more a research topic, but integrating it with the smartphone specifically for the piezo transducers, that has not been done. So this is the kind of future work which we can explore. Okay, now what are the challenges? Finally, I'll wrap up it with the challenges which have not, which are acting as a retaining force for restricting the SHM to reach where it should have reached till now. Because these structural health monitoring projects, actually, they are long-term projects. So for private people, it becomes, many times it becomes difficult to allocate resources for these kind of long-term projects. Then we get huge data. Like I told you, SHM expert needs to convert that huge data into useful information. So that huge data, you should have the capability of converting that data to a useful information, which can only, you just need alarming information. Okay, this is the time, this is not going in the right way. Now it requires some action. Then of course limited budgets. But if you consider the life cycle cost of the structure, I would say this should not be considered as a challenge. Rather, it is the, we need to make people aware that long term life cycle cost of the structure is much lower if you do the SHM of the structures than doing nothing. This is again a very big hindrance, because many times people tend not doing anything rather than doing this complicated, long time structure health monitoring processes. Then this is sort of a political reason, I would say, because for example, fixing the potholes, that has more visibility than doing structural health monitoring. Because if you are doing structural health monitoring, it has comparatively lesser visibility as such. So people tend not to do SHM. Rather, they would tend to fix the problems for more visibility. And finally, people have the tendency to keep doing the things they were doing in past. So they don't, the acceptance of the new technologies coming up is rather comparatively less. So that has to be changed. So in the summary, we have learned about different components of the structural health monitoring, the condition monitoring, structural monitoring, and the structure control, and why it is important. And then different sensor technologies. For example, for measuring the strain, we have electrical and vibrating wire strain gauges. For displacement, we have LVDTs. And what is the reason for the screen rotation of your phone? That's the accelerometer. Then we learned about piezoelectric materials, and in electrological fluids, they are the materials which change their velocity. With electrical field shape memory alloys, they change their shape when they are heated. Chromic materials, they change their color with heat, light, and voltage. Then we learned about global technique and the local EMI technique. In the global technique, the whole structure is acting as a one unit. However, in local EMI technique, only small part of the structure is responding. Then the current status of SHM is that no certification is available. And we also reviewed some of the research work done in SHM. And finally, we learned about the challenges which are acting as a retaining force in the way of SHM. So in the end, I would lastly say that SHM is an easy way to carry out your responsibility towards human life. So we should practice it. Thank you.
Very good presentation, and as I see, madam, from so many messages from the participants, I think, are you able to hear me? Excellent presentation, madam.
Hello.
Hello. Yes. Okay. I hear you now. Can you hear me now?
Yes, ma'am. Yes, ma'am. Yeah, we can take the
Yeah.
questions, ma'am.
So yes, actually, I was just talking to you. First of all, we all need to thank you. It was really an amazing
Thank you.
presentation. We definitely need to connect more to people like you. I think SHM is an opportunity we cannot get everywhere. Uh,
Thanks a lot, ma'am.
I think we have lots of questions, and we are noting them down. However, I think we can take two or three of
Yes.
them.
Yes,
Uh,
sure.
yeah. So one is. Uh, do we use drone technology in India? That's the one that I read.
What is it? Can you come again, please? Do we?
Do we use drone technology in India by Swapnali Kulkarni?
Yes, yes.
That's the one I just read.
Yeah,
Yeah,
definitely. The research work which I showed you, that is done by us in CRRI along with our industry partner. So that we are currently doing in CSIR CRRI. So that work is in being done in India only.
right. Yeah, wonderful. How do we measure ambient vibration?
So there are so many techniques for that. So the traditional way of measuring ambient vibration is the accelerometers, and the other. I'm sorry. You asked the ambient vibrations.
Yes, ma'am. That's the
Uh,
question from the participant.
Okay, I started telling you about the vibrations as such. See, ambient vibrations as such is if it is of that level that our sensors can sense it. For example, many a times we have used piezoelectric sensors for measuring the vibrations caused by the wind. But if the wind speed is very low, we cannot measure it. So we can use the very sensitive accelerometers and piezoelectric sensors, the dynamic measurement sensors for measuring the ambient vibrations if they are of a particular level which they can be measured. Otherwise,
Right,
that noise, that becomes a noise actually, that has to be filtered out.
right. Yeah, so that's why I think Dr. Akshay Das also has asked that how we manage the noise in the data. So what technique you have used to manage the noise?
Uh, um, Generally in our experiments, actually, as per my experience, we first thing which we do is we reduce the noise at the source level itself. For example,
I
we
see.
try to use a electric connection which has a UPS. You always make sure that you do the measurements with the system where the earthing is there, right? So
Right.
this is the cause actually. When I was doing my research work in the IIT Delhi, so almost like 6 months we were not able to see why we are not getting the data in the form which we want. So ultimately, then we came to
Yeah.
know that it was the noise problem, and the power which we were getting, that was not through the UPS. So I would suggest, first thing, you should make sure to stop the noise at the source itself. Then there are so many techniques to reduce the noise. There are so many computational techniques actually through which we can reduce the noise levels.
And then Mr. Madhav wants to know which software you have used for the analysis.
So I always have used the console software, COMSOL. It's a very beautiful software for specifically for the piezoelectric sensors. So, and very its GUI, graphic user interface, it's very friendly. So if you practice a single problem, single example in it, you will be like a master, I would say. So I really recommend you using console software.
Yeah. Mr. Gautam Paul wants to know how much does SHM cost for a typical building and how to approach the expert. Is that something that is in your domain?
Cost estimation. In the
Yeah.
challenges in the last, I told you that SHM, it is different for different structure. That is another reason for not being standard process. For example, in CRRI, we are rigorously using the NDT techniques of rebound hammer, UPV, etc. because they are still standard processes. But if you are talking about SHM as such, so that totally depends upon the structure and what we want, what is the output which we want from the structure. So depending upon that, we will be analyzing the cost. But in a very short sentence, I would say, for example, for the bridges, the center point deflection, the midpoint deflection of the bridge is very important. So if you are not attaching the whole huge sensors, a set of sensors in the system, you at least should go for monitoring the center midpoint deflection of the structure. So that I'm sure that won't cost much. So and if you compare the life cycle cost of the structure, because in case there is a problem in the structure and you have to go for the maintenance, I'm sure that will cost much more in comparison to the SHM cost, which you will be doing in advance to avoid that.
I believe that's also a question of life cycle cost versus immediate. There are just last two questions that I'll be asking. The others we will note down and we may get back to you at your convenient time. So one is, what is the energy harvested in 1 square meter area? Can we also stack up multiple piezoelectric modules for better efficiency over given area?
Yes, stacking has been already explored by many researchers for the energy harvesting purpose. But stacking definitely will increase the energy output. But we are currently actually not going for that stacking part because we are planning to use these sensors in the road surface. So I don't want to go for a solution for which I have to do lot of ground preparation. So what we are doing is we are going for horizontal laying of lot of sensors and we are putting all of them in parallel to improve the output.
Right.
Stacking will definitely improve the energy amount.
Yes. And one last question we can take. Who can look for career opportunities in SHM? How do one start after graduation?
Graduation, I would
Yeah.
suggest to go for training programs. They are in IT also. They are available in. You can come to CRRI also. So we are rigorously into SHM. So if you wish to start, first I would suggest go for some training, or I'm sure in your graduation program there would be some 2 months, 3 months, and there is a 6-month
Yeah.
training course,
Internship.
training program.
Yeah.
So you can first
Yeah.
plan to go for that, and then if you like it, if you are enthusiastic about it, then you should plan for further research in it. But I'm sure this is very challenging actually when you are going in the field work, when you are doing it in the field.
Yes, I believe the theory, communication, and the work with the sensors, etc., is quite interesting and challenging. Thank you so much, madam. We cannot thank you enough for an excellent presentation.
Thank you. Thank
And
you.
yes, thank you, ma'am.
Okay. Thank you so much.
Okay.
Thank you for the attendees also. Thanks a lot. Bye-bye.
Yes, we had almost 168 attendees. Right now we are having 106.
Wow.
But we had almost 168 attendees. So thank
This
you so
was
much.
my first.
I will. Yeah, and it was wonderful. Absolutely.
I was also very excited about it.
Yeah.
Okay, ma'am. Thanks a lot. Thank you so
Okay.
much.
Yeah. Okay.
Yeah, I'm
Yes, ma'am. Yeah. Okay, ma'am.